Welcome to Team WiDrone by Kenton, Lee, Zach, and Yusuf. WiDrone is a lightweight circuit consisting of an inductor coil and rectification/regulation circuit that collects ambient energy from transmission lines and stores it in a drone's battery. WiDrone will extend the drone's battery life potentially indefinitely, allowing drones to fly longer and without the need of a nearby technician. The objective over here is to build a small-scale model of a transmission line to observe the generated magnetic field and the harvestable energy, wind various inductors to test the ideal size, shape, and orientation to find the optimal relationship between weight and surface area and the optimal attachment. Then to design a circuit to rectify, regulate, and charge a standard LiPo battery used to power a drone using the experimentally measured voltage as the standard.
A 7.4-volt LiPo battery was chosen as our standard for this project due to their availability and frequent use. The battery needed a charging circuit which required 9 volts DC to operate. 9 volts was too large of a value to obtain wirelessly, so a DC to DC boost converter was required to boost a much more reasonable 3 volts to 9. The voltage induced onto the receiver is AC, so a bridge rectifier was needed to convert at least 3.3 volts AC to meet the minimum value of 3 volts DC. Finally, we used Faraday's law to find the surface area of the inductor to collect at least 3.3 volts AC within the B field generated by our power line.
For our implementation, we tested the wireless transfer capabilities of our powerline model and the charging capability of our circuit due to the inability to draw the full-scale voltage required to charge the battery. For our model, we have 3 cone heaters that draw a total of 16 amps. Using the oscilloscope, the amount of voltage received by a receiver with 80 turns was measured. For our charging battery test, we fed the charging circuit with a reasonable amount of voltage we would expect to receive from a full-scale power line. To observe the effectiveness of WiDrone, we also measured how fast the battery discharged and charged on our drone.
By placing our coil 1 cm away from our model power line, pulling 15.44 amps RMS shown by the dark blue line, we were able to observe 88.8 millivolts peak-to-peak shown by the light blue line. By varying the orientation of the coil and increasing its size, we were able to observe up to 140 millivolts peak-to-peak. The voltage we see on the oscilloscope is lower than what we originally calculated because it assumes that the coil received a magnetic field at a distance of only 1 cm. We can expect a higher voltage if we implement more turns on the coil and use a thinner wire to maintain the appropriate weight.
Since our model pulled approximately 37 times less current than a typical transmission line in Kansas, we multiplied the 88.8 millivolts peak-to-peak by that ratio to get 3.3 volts peak-to-peak. We then used the function generator to act as the source of voltage replicating what the inductor would generate if it were nearby a full-size power line. We used this voltage as the input into WiDrone and measured the rate that it charged our battery compared to the rate that the battery discharged while flying. We then measured the net charge lost while both were in use and graphed all 3 results. As you can see, the battery uses about half as much as charge while WiDrone is attached, thus doubling the battery life.
To fully charge the battery from 4 volts, it took on average 50 minutes. So to conclude, the battery was successfully charged using the function generator as the source of the theoretical voltage induced by a full-size transmission line. The rate that the battery charged depended on the state of the battery. If the battery was depleted, the battery charged much faster. But when the battery was nearing fully charged, the charging slowed down because WiDrone had a harder time maintaining a voltage higher than the batteries. Our inductor was not able to collect the voltage we anticipated. However, WiDrone was able to charge the battery with the scaled collected voltage even though it was low.
Some of our future considerations would be, first, to replace the proto board with a PCB board with no wasted space, so that the weight could be reduced. The current weight of the WiDrone circuit is 110.3 grams. Another consideration would be to use thinner wires to wind the inductor so that it could further reduce the weight. With thinner wires, we could also implement more turns with the same weight, thus collecting more power. One important thing to be aware of when charging your drone next to a transmission line is to be aware of where the drone is placed when it's charging. In some areas, the magnetic fields will cancel due to the opposing direction of current between the lines, and in some areas, the magnetic field will double because of the induced magnetic field in some regions. So this is our transmission line model built in lab. It's feeding our circuit with 110 volts AC, 60 hertz through our three-phase socket. And now this is our 30 amp circuit breaker, just in case we have overcurrent and need protection. And now the three loads over here. They each draw about 5.5 amps each. So total they draw about 16.5 amps. And that's about 37 times lower than the typical real-life power line, which has about 600 amps. Okay, so now using our model transmission line, we'll now use our inductor to pick up the voltage we get from our three loads. So Kenton right now has the inductor as close to the line as possible, and we'll now look at the oscilloscope reading to see what the peak-to-peak voltage is. So if we look at the peak-to-peak voltage, it's around 75-ish millivolts. There's a lot of fluctuation, but we can safely estimate the voltage received as around 75 millivolts.
So the concept here is when the drone needs to charge up, it flies near a power line. The magnetic field produced by the power line transfers the power to the inductor attached to the drone, which acts as a receiver. The inductor then in turn transfers the power to the WiDrone, which helps to charge the battery of the drone, and then the drone is ready to fly away.
For our battery charging experiments, we have the function generator to replicate voltage received by power line in full scale, which is about 4.2 volts peak to peak. And right now here we have the charging circuit right here and the batteries here. And I will turn on the power source right now and let's see our charging performance. Right now it is charging kind of fast because the battery was depleted. And it's getting slowed down when the voltage gets up. So yeah, that's our battery charging experiment.